So what today we are going to talk about is Compton scattering. It's a process where we can actually see the change in a wavelength of scattered photon. So what happens in Compton scattering is that there is a decrease in energy of an X-ray or gamma ray photon when it is scattered from matter. Say if we take a photon which is having, let's say, wavelength lambda, and it is having such high energy. Now we know that if you want energy to be high, your frequency should be high, or if I want to denote, so frequency will also be high, but what happens to wavelength? Wavelength will be low. So this Compton scattering is not possible via visible light. This Compton scattering is only possible if frequency is very high and wavelength is very, very low, which goes in the range of X-rays and gamma rays. Okay. So what happens in this process is when photon hits material, it kicks out or recoils electron from its original position, and this photon itself gets scattered, but its wavelength modifies. That is the basic difference. That if I have this, so here we will consider that our gamma, sorry, our gamma ray having the wavelength lambda is going in straight line, and then after Compton scattering, it will be scattered with angle phi. So this you have electron which is scattered. So this is your recoiled electron. This is scattered photon. Now from energy conservation, it is obvious that if the energy of the photon is imparted to electron, there will be loss of energy for the scattered photon. So what will happen to the energy of scattered photon? It will be more or less? Less, right? So less energy means greater will be the wavelength. So in order to calculate this, Compton shift is given by where lambda prime is the modified wavelength minus lambda, the original wavelength. And this equation is also called as delta lambda, that is the change in wavelength of scattered photon after it is scattered from the matter, which is given by h upon m into c multiplied by 1 minus cos of phi, where phi is this energy or the angle of scattered photon. Here, this h upon mc is a constant term. So as long as we are talking about electron scattering, this h upon mc will remain a constant. So we can take it as, it is actually called as Compton wavelength of electron and is defined by lambda e, which is given by h upon mc. H is 6.63 into 10 to the power minus 34. M is the mass of electron, 9.1 into 10 to the power minus 31. C is the speed of light, 3 into 10 to the power 8. So this value will come out to be, right here, 0.00243 nanometer. So this, if you remember, your calculations will become very rapid. This is Compton wavelength for electron. So if I rewrite this equation for Compton shift, I can write it as delta lambda equal to, this whole terms become lambda e 1 minus cos of phi. Now looking at this expression, tell me what will be the maximum delta lambda that can be produced in any given situation. What is the largest possible delta lambda according to this equation. When this phi is actually 180 degree. So this will happen if phi is 180 degrees, our cos of phi will become -1 and our delta lambda will become equal to lambda e into 1 minus -1, which will become equal to twice of lambda e. So we know already the value of lambda e. So we can write this as, it will become 0.00486 nanometer. Okay, or you can write it as, because it's really a very small value, we can write it as 4.86 picometer, 10 to the power -12.